So, this is lecture 19 on differentials and constrained differentiation. This is, roughly speaking, pages 212 to 219 of my 2020 lecture notes. And I will just say that, there's far more detail here than probably you need for this course. So I have a lot to say about this topic, but I don't ever tend to test on it quite that much. Let me try to stick with some really simple examples just to give you an idea of how this calculus works. And so here's the basic thing. If I have something like, say, x y squared z cubed equals to, say 1, maybe that describes a surface, right? And I want to compare how the change in these variables interrelates, all right? If I want to describe how the change in x, y, and z are interrelated, what I can do is take the differential of this equation. And so the differential of this equation, what we do is we take partial x and of the expression, and dx plus partial y of whatever it is, And the reason I'm doing x, y, and z derivatives are those are the derivatives, those are the variables which are appearing in the expression. So as a general rule, you just take a derivative with respect to each variable that appears in the expression. So there are 3 variables here, so I've got my differential has 3 terms. Now, this gives me, of course, y squared z cubed dx plus, 2 xy z cubed dy, and then plus, my z cubed has become a y cubed over here. That's bad. Let's make it back to z, plus 3 x y squared z squared dz equals to 0. So this is, I call this, quote unquote, taking the differential of the equation. I took the differential of, let me give it a name, I'll call it Pac-Man. Alright, now the cool thing is you can solve this thing for any variable that you like in terms of the other 2, and that will tell you about partial derivatives. Like, for example, if I solve this for dz is equal to, minus y squared z cubed over 3x, I'm not trying to simplify anything here, y squared z squared dx minus 2x y z cubed divided by, again, 3xy squared z squared, this one was from dy. The minus is because I moved it to the other side of the equation, all right? If you do that, all right, then the really neat thing is the coefficients of the differentials, they tell you what the partial derivatives are of z are with respect to x and y. So like, this is going to be partial z, partial x, and this guy is going to be partial z, partial y, including the minus out front, okay? And then notation that I'm going to explain why we need it. In this kind of context, I like to write a little of y here and a little of x here, just to alert reader x and y are taken to be independent. And you see, well, you're like, well, you solved for dz, but couldn't you just as have well solved for dx? Well, yeah, I could have. And if I did, solve for dx, what would that have given me? Well, solving this equation up here for dx, that's going to give me minus 2x yz cubed dy divided by the coefficient of x, which was y squared z cubed, minus 3 xy squared z squared dz, again dividing by y squared z cubed. And that tells me what the partial derivative is. So that tells me partial x, partial y. I'm holding z fixed. And this one here, again including the minus, is partial x, partial z. And I'm holding y fixed. So this would be, if I write these kind of expressions, I'm using y and z as independent, and I'm taking x as the dependent variable in that expression. So you're like, whoa, well, how do you know which one's dependent and how do you know which one's independent? Well, that's a great question. The answer is you don't. When you face a word problem in engineering or financial math or wherever, you got variables, right? And if you just come to an equation, you may or may not have a clear understanding of which way the dependence goes. Sometimes I have an equation in physics. I always give this as an example. I mean, here's an equation we have in physics. I'm sure you guys have seen it before, right? Like velocity, the final velocity is equal to the initial velocity plus acceleration times time, right? Like, there's an equation in physics. So you could say there's 4 variables here, right? The final velocity, the initial velocity, the acceleration, and the time, right? And so, I mean, you could ask a question like, which depends on which, right? So there's a question. Does the time depend on the initial velocity or the final velocity? I mean, philosophically, I'd like to think that time somehow is set apart from the final and the initial velocity and even the acceleration. But, as far as this equation is concerned, really time is on the same footing as the acceleration, right? So I don't know, like, which is dependent, which is independent? That's a hard question, more of a philosophical question even. And the point is, calculus allows us to take an equation and to take the differential of it, and then you can calculate the partial derivatives with respect to the different variables by just looking at coefficients like that. All right, so that's one of the big calculations in this section. Let me get back to my notes here and just try to be more methodical now that I've got that out of my system. So first of all, I make a definition, tell you what the differential is. If you've got n variables, then you take these n differentials like that. I give you some hopefully nice, man, I'm out of paper. I'm looking for a sheet to cover this with, and I found something. Well, it's got writing on it, but oh well. That'll have to do. Alright, so there's the first example right there. Is, if I've got E is equal to PV plus T squared, then DE would be VdP plus PDV plus 2T dt. I just take the derivative with respect to every variable that appears, right? Just like that. And then here's another one. What is partial f partial x, and what's partial f partial y? If we know that big F is a function of x and y, and we know that df, right, the differential is x squared plus y minus cosine of xy dy. So using the thing I just showed you, we identify the coefficient as the partial derivative. So like partial f partial x will be the x squared plus y, partial f partial y will be the minus cosine xy. Alright? Simple as that. So what I'm trying to tell you is that if you're given a total differential, you can just simply read off partial derivatives. Here's another one. I've got u is this formula, e to the minus t sine of s plus 2t. I take the total differential. This time we've got a ds term and a dt term. And there you go. Of course, you can recognize we just found the coefficients by doing the partial derivatives, so there's that. Here's another one. So these are just some examples of total differentials. Here's an application, example 4.76. If you think about the a spherical shell of outer radius a and inner radius b, the volume is 4/3 pi a cubed minus b cubed. And if you take the differential of that, that gives you a way to approximate, like if you knew the outer radius and you knew the inner radius approximately, like plus or minus a value, you could figure out your uncertainty in the volume, in your understanding of the volume of the shell using the differential, and that's what I do in this example here. So like the total differential is 4 pi a squared dA minus b squared dB. And so like in this problem, the uncertainty in A and the uncertainty in B I gave to be 1 and 2. And so for the numbers involved, the uncertainty in the volume actually would be 62,831.9. Okay, great. In other words, the uncertainty is about plus or minus 6 times 10 to the 4th cubic inches. All right, anyway. Here's another example. W equals xyz. dw is xy dx plus, yz dz. And great. So you could also solve for z. Z is w over xy, right? And then dz would be minus w over x squared y minus w over x squared xy squared dy plus 1 over xy dw. And if you were to solve this equation up here directly for dz, you get this. Now you can compare star, which came from direct differentiation, versus star star, which came from just solving this right here. Solve for dz. So you notice the difference here? Star we obtained by first solving for z, then doing the differential, versus taking the differential first and then solving for dz. Two different ways to calculate dz. It would be somewhat disconcerting if we got inequivalent answers, right? That would be annoying. And it looks like we got different answers, doesn't it? Look at that, Those formulas don't match up, do they? Or do they? See, they appear to be different, but they're actually not, because if we take w over x squared y here, that's actually z over x. And likewise, so if you use the defining equation w equals xyz, you can convert the coefficients to match up, right? All right. So anyway, let's get back to that dependent versus independent. I have an example I show everybody who takes Calculus 3 with me, because this is a point which is neglected in usual books, and it's unfortunate because it actually matters. So in this example I just went over above, which variables were independent, which variables were dependent. The initial portion of the example I said I treated xyz as independent, whereas w was dependent, but then the last half I thought of x, y, and w as independent, and z was the dependent variable, right? So check this out. If we ask what is the value of partial z, partial x in the above example, it's ambiguous, right? Because in the first part of the example, rather in the latter part of the example, oh goodness gracious. Yes, in the first part of the example, when I first had dw is y dx plus x dz plus, let me say it this way. When x and z are taken as independent variables, then essentially by definition, partial z, partial x is 0, right? But if z is taken as the dependent variable, then partial z partial x, well, it is minus z over x we found right here. So which is it? Is partial z partial x 0, or is partial z partial x minus z over x, right? You're like, what? Well, that's why at the start I was saying we should tell the reader what our independent variables are. Then we can avoid this kind of conundrum. And so the solution is simply that, like, partial z, partial x, holding y and z fixed, that's equal to 0, because x, y, and z are the independent variables. But this one was a different thing. That was partial z partial x, and there we were holding y and w fixed. Y and w were the rest of my variables, and so they're different partial derivatives. And so this is the problem of constrained partial differentiation. When you have an equation which you're stuck with, and then you have to study the rate of change of variables with respect to each other, and there's an ambiguity involved, like which are the dependent, which are the independent. Well, we have to make a choice, and once we make that choice, then the partial derivatives are unambiguous. But until we make that choice, it might not make sense to say, what is partial z partial x? Well, in the context of the example we just went over, it could be two things. At least two things. So here's a comment here. If here's a more explicit version of all this. Here's a sort of abstract. If we have x, y, w, x, y, and z are variables, then we could write dw as partial w partial x, partial w partial y, partial w partial z. And in each one of these, we're holding everything else fixed. So each one of these, I've got xyz, yxz, zyx, zxy. So basically, the notation here explicitly indicates that x, y, and z are the independent variables in the first differential. Whereas if we were to look at dx being arising from changes in w, y, and z respectively, then we're taking w, y, and z as the independent variables in this expression. See w, y, z, y, w, z, z, y, w. Yep. Let's see if I have another example. All right. All right, so yeah, and it can be that, so my next example is actually the next sort of stage in this game, which is, what if you don't just have one equation? What if you have two equations, right? And so here I've got w equals x plus y plus z, but I've also got x plus y equals wz. Now there are two equations constraining the derivatives, and the question is, what's partial w partial x holding y fixed? What's partial w partial x holding z fixed? So step number one, I suppose that w and x both depend on, rather w and z both depend on x, y. And so partial w partial x is partial x holding y fixed of x plus y plus z. So in this context, partial y partial x is 0. Partial x is 1. Partial z partial x, well, we don't know. But partial z partial x holding y fixed is that. And then I substitute in w equals to x plus y equal to wz to get this, which tells me that dx plus dx is that. And then I plug that in. And therefore, so what I'm doing is trying to find I'm just sorry guys, I'm not sure why I did star here. I mean, I could have done star star without doing star, I think. anyway, let me not belabor this point. I don't want to take up too much of your time. The bottom line is I calculate partial z partial x holding y fixed as 1 minus z over 2z plus x plus y. And returning to star. I'm an idiot, guys. I'm just not seeing things clearly. Look, this says that partial w partial x is related to partial z partial y by adding 1 to it, right? So I figured out that I could calculate partial z partial x holding y fixed by this argument here, and I got that, right? But then to get back to what I wanted, which was partial w partial x holding y fixed, I take 1 plus this, which gave me that. Great. Bottom line is these ones that have two equations, it's kind of like two equations and two unknowns with some calculus mixed in. So the other derivative I asked for was partial w partial x holding z fixed. So I start out the same way. I differentiate the w equation, and this time holding z fixed, right? That means that partial z partial x is not automatically, no, partial z partial x is automatically 0 because this says x and z are independent. So that term is 0. The partial y partial x survives, and we still have 1 from the partial x partial x. And so I need to calculate partial y partial x from the other equation. So I used the star thing I derived before to get me partial y partial x holding z fixed is just 1. And consequently I get partial w partial x holding z fixed is 2. So again, just to illustrate, partial w partial x is this, partial w partial x is that. And as you can see, they're not equal because they're not the same partial derivatives, really. One is taking x and y to be independent, the other is taking x and z to be independent. So calculus books have problems in them which are based on this this abuse of notation. So like here's a pretty popular one. Here's the ideal gas law, PV equals nRT. So if we calculate partial v holding t fixed, we get minus nRT over v squared. And if you calculate partial v partial t holding p fixed, you get, I'll get it in frame eventually here, you get nr over p. And if you calculate partial t partial p over holding v fixed, you get v over nr. And if you put those together, you have partial p partial v holding t, partial v partial t holding p, partial t partial p holding v, and multiply those together. You might expect that you get 1 because you can kind of think about the partials canceling, but it's not the case. Actually, when you put the calculations we just did together, you get minus nRT over v squared times nr over p times v over nr, and things cancel and leave you with minus nRT over pv, which is of course minus 1. So this is an example where naive cancellation of partials fails. Here's just some more general patterns to look for. If you have a level surface, f of x by z equal to 0, we can calculate the partial derivative of x with respect to y holding z fixed, or y with respect to x holding z fixed, or z with respect to x holding y fixed. All these different partial derivatives we can see from simply solving the differential of f equal to 0, either for dx dy or for dz, and reading off the corresponding coefficients. So that's kind of cute. And this is just the generalization of the previous example. If you calculate partial x partial y times partial y partial z times partial z partial x, holding respectively z, x, and y fixed, you get from this right here, minus fx. So let me show you where this is coming from. This guy, which is this guy, right? Where's that coming from? That's from the dx, right? That's this right here. When we look at dx and we look at the coefficient of dy, that gives me that partial derivative, right? When you look at, come on, the partial y partial z holding x fixed, that's going to be from dy. That's that's this one, fx over fy. What? Oh. Oh, that's a typo is what that is. Oh no. Should that be fx over fy? No. That's fz over fy as it appears correctly over here, right? Fz over fy. And then finally, grief. It's the idiot who wrote these notes. All right. And then partial z partial x, this guy, right? That I can get from looking at dz, looking at the coefficient of dx. This one. And then, of course, that's the fx over fz over here. There's actually a minus on all three of them. So it's minus, 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 and the product of the three minuses gives me minus again. And, of course, they cancel as well, right? Like the fz with fz, the fx with fx, the fy with fy. That's how it goes. And you can actually use example for this example to calculate partial derivatives for like a level function. It might have an example like that here. Oh yeah, here's one. So suppose you've got x squared plus y squared plus z squared equals to -1. If you wanted to calculate partial z partial y, you could say minus fx over fz, which is minus 2x over minus 2z, which is minus x over z. You could do it like that. You could memorize that formula and use that as a method to calculate that. But honestly, I would really be happier if you just understood that you can take the total differential, 2x dx, plus 2y dy, plus 2z dz. I mean, you got a formula sheet, so it doesn't really matter in terms of like how you remember things, right? But man, I much prefer to look at like this, and then so, you know, dz equals minus x over z dx minus y over z dy. And see, from that one little purple calculation there, that little purple calculation right there, I can immediately read off that minus x over z is my derivative of z with respect to x. And oh, that's what I actually do down here. If I could read my own notes, that's what I show down here, is that you could just as well read it off. Two things at once, actually. This gives us two derivatives for the cost of one differential calculation. Here's the corresponding trick problem for a level curve. If you calculate partial x partial y times partial y partial x for a level curve, you get 1, because you get minus 1 times minus 1, which is 1. And here's a picture of a level curve with the gradient vector field. Great. And anyway, I have some more complicated examples of constrained partial differentiation in what remains of this section. I'll let you look at them if you want. These are essentially homework problems that I found in Stewart's calculus that I worked out, and you know, yeah, they're what they are. And finally, just a a mention, shout out to Advanced Calculus here. Really, the fact of the matter is that all of these derivatives we're taking, they only make sense in the context of, can you write one of the variables in terms of the others, right? And the answer to when that is or isn't possible is, in fact, told to us by something called the implicit function theorem. And so hopefully I'll get back to that at the end of your analysis course, so I'll leave it for there. But anyway, I hope you see how to do the calculations here. It's actually, really, if you understand how to take that total differential, and you can embrace the interpretation I tried to share with you here, in terms of you just read off the coefficient to get the partial derivatives, it's as simple as that. So I hope I've done enough here to make it make sense for you. And if not, it's, there are certainly more important topics for your next test than this. Like the last lecture on tangent planes is much, 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 much more important than this. So anyway, I'll say that. Thanks, guys.